We do it 100 times a day. Flip a switch and the lights come on. Plug in a phone and it magically starts charging. Electricity is just there. It's the lifeblood of our modern world. But have you ever really, truly stopped to think about where it comes from? Well, today we're going to trace that power all the way back to its source.
Right, so when you flip that switch, you're tapping into this gigantic, invisible network. But that network has to start somewhere. And the real story, it begins way before any wires get to your house. It starts at a power plant with a process that's just massive in scale, but also surprisingly simple at its very core.
And that's it. That's the big secret, right there. It doesn't matter if we're talking about burning coal or splitting atoms or even harnessing the wind. In almost every single case, the main goal is just to make something spin. This one, simple, mechanical action is the key to unlocking all the electrical energy that runs our lives.
Yeah, it feels like magic, for sure. But it's not. It's really just the result of some incredible engineering, all built on a basic law of physics. So, let's pull back the curtain and take a look at the machine that makes the whole thing possible.
Okay, meet the hero of our story, the generator. This machine, or something like it, is at the heart of pretty much every power plant on the entire planet. It's the essential link that turns spinning simple into the electricity we use. So how on earth does it work?
Well, it all goes back to this brilliant guy named Michael Faraday, way back in 1831. He discovered this thing called electromagnetic induction. Basically, he figured out that if you just move a magnet near a coil of wire, you can actually push the electrons in that wire and make them move. And what is a flow of electrons? That's it. That's an electric current.
So a modern generator just takes that idea and scales it way, way up. You have some kind of energy source, we'll get to those in a second, and its job is to spin a rotor. Think of a rotor as just a big magnet on a stick. As that magnet spins, its magnetic field flies past all these stationary coils of wire. And just like Faraday found out, that motion pushes the electrons in the wires, and boom, you've got a powerful current. It's that simple. Motion in, electricity out.
Okay, so if we know we need to spin a generator, the next obvious question is, how do we actually do it? This is where all the different kinds of power plants come into play. They're all just clever, different methods for creating that one essential spinning motion.
For more than a century, the most popular answer has been to just boil water. I mean, it sounds simple, right? But if you can create really high-pressure steam, you can use that steam to blast against the blades of a giant pinwheel, which is called a turbine. If you get that turbine spinning, you just connect it to a generator and you're in business.
So here's the classic setup you'd see in a coal-fired power plant. You burn coal in a boiler to make a ton of heat. That heat boils water into high-pressure steam. That steam shoots through pipes, spins the turbine is connected to the generator, and just like that, you've got electricity heading out onto the grid. Now here's what's so wild. A nuclear power plant works on the exact same principle. The only major difference is where the heat comes from. Instead of burning coal, a nuclear reactor splits atoms, a process called fission, to generate a truly incredible amount of heat. But after that part, it's the same exact story. Heat boils water, steam spins a turbine, and the turbine spins a generator. And the reason nuclear is so powerful is its mind-boggling energy density. I mean, just let this fact sink in for a second. A single, tiny uranium fuel pellet, about the size of the tip of your pinky finger, has the same amount of energy as an entire ton of coal. It's just an amazing way to harness the power locked inside an atom. So, making steam is a really effective method, but it's not the only way to do it. Some power sources just skip that middleman entirely and use the raw power of nature to spin the turbines directly. Take a hydroelectric dam, for example. Here, we're literally using the force of gravity. By building a dam, you create this huge reservoir of water up high. When you open a gate and let that water rush down through a pipe, its immense weight and pressure spin a turbine directly. No fuel, no fire, no steam, just the pure power of falling water.
And wind turbines? They're even more direct. They're really just high-tech windmills. The wind pushes against these huge, specially shaped blades, making them spin. That rotation turns a generator that's housed way up at the top of the tower. It's a really elegant way of turning the movement of air directly into electricity. So far, we've got a pretty clear rule, right? To make electricity, something has to spin. But, in science, for just about every rule, there's always a really cool exception. And when it comes to energy, that exception is solar power. This is a total game changer of a question. For thousands of years, making power has been about mechanics, wheels and levers and spinning things.
But solar panels, specifically photovoltaic panels, they just throw all of that history right out the window. They do something that really does feel like magic.
And here's how they pull it off. It's called the photovoltaic effect. When photons, which are just particles of light from the sun, hit a solar panel, they literally slam into the silicon atoms inside and knock electrons loose. The panel is designed to herd all these free electrons into a circuit, and that creates an electric current. No noise, no fuel, and, crucially, no moving parts. Just sunlight turned straight into electricity.
Okay, so we've got all these different ways to make power. Some use steam, some use wind and water, and one doesn't spin anything at all. So why don't we just pick the best one and use it for everything? Well, it turns out each method has its own unique set of pros and cons.
First, let's look at how reliable they are. We measure this with something called a capacity factor. It's basically just the percentage of time a plant is running at full power. And look at nuclear. It's an absolute workhorse, running over 90% of the time, providing that steady, constant power. On the other end, you have renewables like wind and solar, which are what we call variable. They only make power when the sun is shining or the wind is blowing.
Next up, environmental impact. And on this front, the difference is night and day. Burning fossil fuels like coal and gas, as you can see, releases massive amounts of carbon dioxide. But then you look at nuclear, wind, and solar, and they generate electricity with virtually zero CO2 emissions while they're running. That makes them incredibly important tools for tackling climate change.
But of course, there are other trade-offs, like how much land they use. Sources with high energy density, like nuclear and coal, can generate a huge amount of power on a pretty small piece of land. Renewables, on the other hand, are collecting energy that's more spread out, sunlight and wind. So you need to cover a much larger area to get the same amount of power.
So, after looking at all these incredible technologies, from burning rocks to splitting atoms to catching sunlight, we can come right back to where we started. Our entire electrified world is pretty much built on one simple, elegant idea: creating motion.
This quote just sums it all up perfectly, doesn't it? It doesn't matter if it's a coal plant from the 19th century or a wind farm built last year. They're all fundamentally in the same business. They're all just different answers to the same question. How do we spin a generator?
So the next time you flip on a light, just take a second to remember that incredible journey the electricity took to get to you. It almost certainly started with something spinning, somewhere out there. And as we look to the future, the big question isn't if we'll spin generators, but how we'll choose to do it, to build a cleaner, better world. What choice will we make?